Bismillah ar-Rahman ar-Rahim. Good evening, everyone. Today, our lecture will be on the interesting article. This article's name is The Influence on the Central Temperature, Bone Structure, and the Magnetic Properties of the Manganized. All of these two structures, A and B. The doping ratio will be changed between these two rings, A and B. The first one will be equal 0.05, the second equal 0.25. The doping element will be the silver, the Ag, like we are seeing now. It's very interesting article. Our target here is by increase or by use different high temperature. What will be on the structure, specifically on the grain size? By increase the doping ratio, any change will happen on those. Let's take deeply look by using the next slides. Maybe I prepared 35 slides or something like that. Let's start with our lecture today. Let me change this slide. Yes. Now, it's the first slide, the influence on the, here it's the outline. We'll explain the important information about this article, the influence of central temperature on the structure and the magnetic field by using the doping element is silver. The doping ratio, we will use two different doping ratios. We'll take a simple idea about the double exchange mechanism, the salt gel process here. What is the salt gel process? By using some good pictures from my works to help us to understand the main idea, the experimental details deeply, and the cure temperature and its relation with the doping ratio. Here, like we know, the parent structure is AB03. All of AB are cation or 1,3 atom of oxygen, specifically 3, no more, no less, because that's mean we will deal with another structure. Here, lanthanum manganite oxide. Lanthanum is an alkaline earth. Manganite it's belong to transition material group. And we know the perovskite dioxide at itself, it's an isolator. It's antiferromagnetic. Because that we do this doping process to can reach conductor, you can reach paramagnetic, and some tracks to can make that happen near from room temperature. Now let's take an idea about the electrons, the shells in the ferromagnetic. Ferromagnetic compounds of manganese with perovskite structure must know some important notes about from this. I take this from abstract about source number 12. The 3D electrons available contributes with their spins to the saturation manganites or magnetization. The 3D electrons are available to contribute with their spins to the saturation magnetization. And let's say what is the magnetization or ferromagnetic properties. Ferromagnetic properties is interaction between the weak manganese 3+ with negative manganese 3 plus 4 plus. And we can say a strong position to manganese 3 plus 4 plus. It's the same name, it's the same meaning with ferromagnetic properties, something like that. All of these is the interaction, the results from interaction between weak manganese 3 plus 3 plus and negative manganese 3 plus 4 plus. And from our article, not our article, from this article about the effect of centric temperature on the structure and magnetic properties, the recent investigation have shown high enough magnetic polarity effect and this costly manganite compound such this doping perovskite oxide compound, no structure. Here, this structure, doping structure, proposing their potential applications because that's important, because we can use it in ferromagnetic or refrigeration magnetic applications around or near from room temperature. Now we know A is alkaline air, and we have two kinds of it, monovalent 1 plus and divalent 2 plus, such as calcium, strontium, barium, lead, silver, potassium, and we can use another, with this compound, we can use another transition material like iron, manganites, something like that. It is known that this structure, the doping structure, perovskite oxide, and let me say the magnetic properties are favored by alkaline earth side doping. Here the element table, the periodic table. When I said alkaline earth are here. Rare earth at above. Sorry, below here. And all of these are transition materials. Here are alkaline air cation substitutions exchange for lanthanum in the structure of the structures gives rise to interesting to the magnetic and structural properties and electrical properties. Here, all of the monovalent and divalent lanthanum improves what? Improves the magnetic properties, higher Q temperature and magnetic local electric resistance according to the double exchange. Here, the lanthanum, like I said before, monovalent and divalent lanthans. These ions, plus 1 plus, it's very important in double exchange, and we will talk about that. At source 15, interaction between the D shells and the transition metals is assumed what? This interaction between D shells and the transition metals, not in alkaline earth, not in rare earth, specifically in the transition metals, D shells interaction in the transition metals. Transition metals, the elements which are in the middle of periodic table. First one, the interaction between the incomplete D shells, incomplete, not complete D shells of transition elements is insufficient to cut, to disrupt the coupling between the electrons in the same shells. We have interaction about many D shells. And now we talk this interaction between incomplete D shells, that means I have many shells of transition element, is not enough to cut the D electrons, not enough to cut the coupling the bonds between the electrons and yes, not enough, let me say, to cut the bond between the d electrons in the same shells. The spin coupling between the incomplete d shells and the conduction electrons leads to what? Leads to tendency for a ferromagnetic alignment of the spins. Here, the last line is very important. Since each monovalent silver oxidizes what? Oxidizes two manganese 3 plus to the manganese 4 plus ions that is favored by double exchange mechanisms. It's the double exchange mechanism specifically about how we can some electron jump from above shell from manganese to manganese to make the ion positive number change by using the oxygen between them like a bridge. Here, an electron maybe. Let me explain this example by using this image. It's easier, I think. Consider this degree 108 interaction between manganites, oxygen, manganites, in which manganites at Eg, that's at above shell, above orbital, when we have one electron here and we have empty here, are directly interacting with oxygen at 2p, specifically at this place. This electron will jump like that from this side to its head to down like that by using this electron, this oxygen to say another station from its trip with the oxygen orbital, and one of the manganese ion has more electrons than the other. I mean, here we have one, here we don't have, because that's here we say 3 plus. Why? Because the manganese it's full with 7 electrons. When I have 4 electrons with negative signs, that means I have 3 empty places with plus sign, with positively sign. Because that, here 3 plus, here 4 plus, this electron will travel to another manganese to change its ions number, but by using the oxygen like the next station, and after that keep going to complete its trip. But by very clearly, very sensitively with the hands rule, because the electrons will change his direction, spin direction to one time, specifically at the oxygen station. And after that, we'll come back like that. And here has more electron than the other, and the ground state at this place here, all of these have 3 electrons at the same spin direction. The oxygen gives up its spin of electron to manganese. Its vacant orbital can then be filled by an electron from manganese 3 plus. That's new. This electron will jump from manganese to manganese by make this trip contained from 2 steps. Other one, the first one to jump to oxygen, the second one to jump to another manganese and change its manganese ion sign. Okay. At the end of the process, our electron has moved to the neighboring metal ions, retaining its spin like that. This is very important phenomenon to us are perovskite oxide has a big actor, a big effect on the perovskite oxide properties. The double exchange predicts electron movement from one species to another will be more easily if electrons don't have here. We talk about the Hans rule. More easily if electrons don't have to change the spin direction. That's mean by the Hans rule, the electron can jump from manganites to manganites easily than we don't pay attention or don't have the Hans rule. In order to conform with Hans rule when on the accepting species, it's easier because the Hans rule and it decreases the kinetic energy, the ability to hop, the jump from manganites to manganites, play, act, play rule, play bad rule, because it's work to make the kinetic energy be less and less. Here, now let's us talk about the experimental procedure, specifically in the lab. How we can, or how the research could produce this to perovskite, doping perovskite oxide by using the Ag, the silver light doping element with two different doping ratio. Here, the present study aims to explore the effect of Ag extraction and by using three different high centering temperature on the system. Here we have two doping ratio, like I said, being prepared by sol gel method. Sol gel method is a chemical process, easy and cheap chemical process. By using it, we can introduce the nanoparticle size, and has some advantage, like it's cheaper, cheaper than the other ways have the same target, and at the same time we can say can work with temperature lesser than the others way. Here, this doping perovskite oxide contains are lanthanum oxide, silver nitrate, and manganese nitrate. All of these were dissolved on dilute nitrate acid, at which temperature will start to work at 150 Celsius. Then citric acid and ethyl glycol were added like agent to make the nanoparticle increase more. This way, used the chemical researchers to increase the nanoparticle from number to number. Like I said, some articles would increase the nanoparticle by using these agents, I mean the citric acid and ethyl glycol, from 70 nanoparticles to more than 120 or something like that. That's mean why we use the citric acid and ethyl glycol, because it's a good agent to increase the nanoparticles as can possible. Here is the centering device. By using it, we can mix all of these contains. I said it before. By using this device and put small thing, this thing is the magnetic fish. By using the This center device has a furnace, a small furnace, and at the same time has a magnetic field. By using the magnetic fish, we can put it, we can centering the this liquid to conjugate our mixture. At the same time, we can increase the temperature to not too high temperature, but we can start from 100. In my works, I started from 100 Cs, but here the researcher started from 150. Here from 150, and by using this magnetic fish, by using this device, they could, let me talk more specifically, the researchers could reach the dense solution. Here, viscous residual was formed. Something like honey, like foam, viscous, formed by slowly boiling the solution. That's mean increase the temperature more from 150 to 200. And the obtained residual was dried slowly at 300 Celsius. Here, from 150 to 200, you can reach the general form, is something like honey or food, like these two pictures above. Until here, the magnetic fish can move, but when increase the temperature more and the liquid started to be something like yellow, it's difficult to the magnetic field to move anymore. After that, they try to dry this gel. Dried from what? Why? I'll explain that in the next slide. Until dry gel was formed like honey at 300 CLZ. Here, the researchers could from the dry to dry the gel. Dry the gel, and after that, they will fire it, because that's not enough. The residual processes was burned in air at 600 CLZ in order, why? To remove the organic materials from this chemical liquid. It's used during chemical reactions. When these organic materials are produced, they are produced during the chemical reactions to all of these contents. Because that we need to remove all of these organic materials, because that we will burn all of these. Here, the first picture less than 600 by using another another furnace. You can reach less than 600 CZ, and after that put it in another bigger furnace. You can reach 600 CZ. You can produce the samples, the very tiny samples. Here, fine powder. To have fine powder, grinding process. That means something like this to destroy these grains size more and force it to make aggregation, or let me say, force it to make groups and make the distance between all of these grains be less and less. By using what? By using a gate mortar. This gate mortar. This tool is a gate mortar to make the grinding process. But at first, we must clean all our tools by using alcohol, some strong chemical liquid to clean our tools. Here, Three sets of pellets were produced from each composition by pressing into 13 millimeter radiant, 2 millimeter thickness under 3 tons. This, the pressure device under 3 tons, the researchers could produce the tablets, okay, the samples. This the scaler to can specifically know how much gram we put it. Here, 2 millimeter thickness, 13 millimeter radii under 3 tons to produce tablets. 3 tablets, I think, something like that. Because we have 3 different centric temperature, 3 tablets to each doping ratio. Each pellet set was then separately centered at these 3 different temperature at a day, 24 hours, and leave it after that to reach the room temperature. You can touch it, you can use it, you can put it. Here now let's talk about the results and discussions. At first, we need to take the atmosphere macroscopic and scan electron macroscopic pictures to all of these samples services. You can take ID, you can take a look, you can take about the grain size will is decreased or increased, and the Ag concentration has any effect on the grain size or more, which of, and another diagram we will talk about which one the curve will be near from the room temperature. Results and discussions, atmosphere's microscopic analysis before skin. The first picture is before the central temperature, before the 1,000, 1,200, or 1,400. That's mean what? That's mean at 600 Celsius. The grain size like that, and the nanoparticle size from 0 to more than or approximately 200 nanometer. Okay, here image of before center. Before center. What that's mean? That's mean at 600 CZ, the soldier prepared samples have 4 nanoparticle size particles, like I said before, each from 100 to 200 size particles gather as groups come together, collect together as groups in the structure, but not more than 200 nanometer. And you will see in the next emails, this number will change by increasing the cure temperature, and will change or not with the doping ratio. Here, from 600 to the doping ratio, 0.25, at 1,200, the grain size be like that. From 0 to 800 nanometers. That's mean multiples to approximately 4 times are given here in figure number 2. Not 200 anymore. Here the number is 800. That's mean multiple to 4 times. The grain size is multiple to 4 times. But at when increase the temperature to be more than 200 CZ to be 1,400, the grain size reached to be 1.2 micrometer, not nanometer. That's need to 10 force -6, not to 10 force -9 anymore. That means it's a huge increase in the grain size from 600 to 1,400, and increase the huge increase to from 100 from 1,200 to 1,400. Here nearly from 1,200 to 1,400, it's nearly to the grain size is multiplied to 3 or 5 times more increased. Here we will see something like strange materials. We will say something like impurity, where between the grain barrier, grain boundaries, sorry, between the grain boundaries, we will see a strange, here we are seeing a strange particles where between the grain boundaries. Why? What is between the grain boundaries? Give the opportunity to these materials to be here. What is this material? What are these materials? Here materials are the metallic silver particles. And increase the temperature to very high number, this Ag particles will far away. Let me come back to these slides. An increase in central temperature, like I said before, and a growth of grain size for both Ag concentration, all of the different ratio concentration to silver, the grain size in it will increase with increase the centering temperature. But the Ag concentration will not take a huge change like the grain size. And sorry, the grain size, let me say that by using easy words. How I can say that? Let me say the Ag, the grain size will not face a huge change when increase the Ag or the doping ratio. Very fine particles were observed at the grain boundaries in figure number 2, like I said before. It is very likely that these particles are metallic Ag particles, like I said before. The grain boundaries of polycrystalline materials are the place, the grain boundaries are the place to these metallic Ag particles to stay in it. Where the why we have a reason because between and at the grain boundary the surface energy is minimum because the metallic doping particles will take opportunity to kind of travel, to kind of escape from high temperature to be at the grain boundaries. For this reason, these places are most likely locations for axes Ag that leave the perovskite structure under high temperature. That's it. Our lecture is done. I will the part number 1 from this lecture is done. See you at part 2 from this discussion. Let me say in our lecture. Okay. Thank you about watching. Go listening. Have a good day. Part number 2 will talk about more deeper about the image, the scan electron microscopic and atmosphere microscopic, and we will talk deeper ideas about the scan about the X-ray diffraction, and the last and other information about until the conclusion from this article. Thank you so much. Have a good day. See you soon. Let me stop recording. End.